All right, so in this problem, we're gonna solve problem 215. This is 222. We're gonna solve 215 using the potential energy approach. And it's kind of cool, it's kind of complicated, but I think it's pretty cool how it all works out. But let's go ahead and get started. All right, so here's the deal. I'm gonna do this problem up to this step right here, and then after that, just like I did the other one, I'm gonna put in the description the other video where I do solve it completely right, because we're just solving, in this case, 215 using the potential energy approach, but I already did it solving the direct stiffness method, so it's all the same once you get to this part. That's when you could just watch the other video, but just to save time. So again, these problems, the overall goal is to get the total potential energy of the system, and that is the internal strain energy of every spring plus the potential energy of the forces acting at the nodes. So usually this term right here will have one more term than this one, but again, there are cases where you'll have equal number of U's and omegas, and then in some cases you'll have more U's than omegas, but usually you have more omegas than U's. So in this case, there's 1, 2, 3, 4 nodes. So that means this term right here is going to have 4. And then this term is going to have 1, 2, and 3. 3 springs, so 3 terms. And that's pretty easy, right? So the first term for U1, it's going to be, I'm not going to go into the theory either, but for a linear spring, we assume they're linear unless they say non-linear, but for the most part, they'll be linear. U is equal to 1/2 kx squared, right? There's theory behind it, but I'm not going to cover it in this video. And then for omega, that is equal to negative force times displacement. So U1, right, of the first spring, let's go ahead and label this 1, 2, and 3. It's 1/2, right? We're just using this formula, 1/2 kx squared. K, we'll put K1, and X is just the displacement after, I guess in this example, there's 4,000 newtons going to the right at node 3. So this is gonna move, obviously, right? Once you apply a force here, it's gonna move this way, and we're gonna find the displacement between every single 2 nodes. So between these 2 nodes, between these 2 nodes, and between these 2 nodes. So for the first one, right, it's 1/2 K1, first element, and then the displacement will be the distance between U3 minus U1. U3 minus U1 squared. Again, that's just 1/2 kx squared, if you could see it. Similarly, for the second element, it's 1/2 K2, and it's between nodes 3 and 2, so U3 minus U2 squared. And for the third one, it is between nodes 4 and 3. It's 1/2 K3, and that is U4 minus U3 squared. Okay. For the omegas, they're pretty straightforward. It's just the force times displacement acting at each node. So I'll go ahead and just write omega for all of them. Omega is going to equal negative F1x U1 minus F2x U2 minus F3x U3 minus F4x U4. Okay? So we could go ahead and assemble this pi p equation, the total potential energy of the system. That's going to be, let me do this, pi p is equal to 1/2 K1. So it's just the sum of all the U's, okay, for the first U term. So this U is equal to U1 plus U2 plus U3. So I'm going to go ahead and just start writing them down. 1/2 K1, and I'm going to go ahead and do the FOIL method. So it's going to be U3 squared minus 2U3U1 plus U1 squared. Now for the second one, it's going to be 1/2 K2 times u3 squared minus 2u3 u2 minus plus u2 squared. Okay, next one, plus 1/2 k3, that is u4 squared minus 2u4 u3 plus u3 squared. Be very careful, it's easy to make a mistake in these. But continuing it, now that we added all the three u terms, now we just add the omega. So in this case, it's minus f1x u1 minus f2x u2 minus f3x u3 minus f4x u4. Okay. Let's simplify it a little bit more just to make the equation easier, unless you know how to take partial derivatives with respect to each displacement, because that's what we're going to do after. But I'd like to go ahead and just kind of multiply this out to all three terms for every single one. So it's going to be 1/2 k1 u3 squared minus k1 u3 u1 plus 1/2 k1 u1 squared. I just multiplied this term to all these three, and I'm gonna do the same for everything pretty much. So plus 1/2 k2 u3 squared minus k2 u3 u2 plus 1/2 k2 u2 squared. Awesome. Okay, keep it going. 1/2 k3 now times u4 squared minus k3 u4 u3 plus 1/2 k3 u3 squared. Right? Hope I didn't mess up there. Verify this, okay? But I'm pretty sure it's right. Minus f1x u1 minus f2x u2 minus f3x u3 minus f4x u4. Okay, so we're right here. Now that we have the term all nicely laid out, we could go ahead and start taking the partial derivatives of the potential energy equation with respect to each node. Not node, displacement at each node. So in this case, let's do u1, and that's equal to 0. Why do we do this? If you'd seen the other videos, 218, it explains that this is where the minimum potential energy occurs for, I guess in this case, in each spring. But that's why we do this with respect to each node, okay? It's not because it just works. But when you do it with respect to u1 of this whole equation, there's no u1 here, so that goes to 0. There's one u1 right here. So it's going to be negative k1 u3, right? Because when you take a partial with respect to that variable, it's like taking the derivative of 2x with respect to x. The answer is just 2. So in this case, u1 just went away. Take the derivative here. That 2 gets multiplied to the half, so it becomes plus k1 u1. There's no u1, no u1, no u1. All these 1 is 0. There's one right here. So it becomes minus f1x, and that's it. Next one. Now we do it with respect to u2. I'll be honest, whoever figured this stuff out, man, that's some crazy engineering right there. Because it makes sense, you know. It works out every single time. So with respect to u2 now, nothing here, nothing here, nothing here, nothing here. There's one right here, u2. So that is negative k2 u3. There's one right there. That becomes plus k2 u2. None here, none here, none here. That's it. Minus f2x. Cool. Next one. With u3. All right, and that is equal to 0. So look for the u3s. There's one right here, the first one. That's going to be k1 u3 There's one right here. Minus K1 U1. Okay, there's nothing here. There's one right here. That is K2 U3, right? Plus K2 U3. There's a U2 right there. Minus K2 U3. Oh, hold on. Minus K2 U2. So, yeah. We're taking it with respect to U3. So, this goes away. So, it's negative K2 U2. Plus, no, nothing there. Nothing here. There's a U3 right there. That becomes negative K3 U4. There's a U3 right there. That's plus K3 U3. Cool. Minus, finally, F3X. And then, finally, with respect to U4. Let me move it up. With respect to U4, okay? So, that's equal to 0. Now it's gonna be U4, nothing here, nothing here, nothing here, nothing here, here, right here, first one. It's K3 U4, okay? Then minus K3 U3, okay? No U4 here, cool, minus F4X. And it kind of makes sense. You might not know this at first, but the fact that the third node has so many terms is because the third node is interacting with every single other node. So it makes sense that it has the most terms. I guess that's something you'll kind of just figure out as you go along, but just FYI. All right, cool. So now this is what I'm gonna do. Look, I could technically go straight to the answer, but I'm gonna do one more step. It doesn't take too long, but it's gonna help you see it. If you still have trouble with matrices, this is gonna help you see the answer. So I'm just gonna rearrange these 4 equations so you could see the matrix form. F is equal to KD, right? So I'm gonna move all the forces to one side. It's equal to 0, remember. So I'm gonna move all the forces to one side. F1x, F2x, F3x, and F4x equals. Okay, now check out what I'm gonna do. I'm gonna do the first column of the matrix, okay? All the U1s will go here. So anything that has a U1 in the equation, it's gonna go here first. So check it out. There's a U1 right here, right? That constant in front of it is K1, so I'm gonna put K1. Is there any more U1s in the first equation? No, right? So that's it, close it up. Second equation, there is 0 U1s, right? Hold on, we did something wrong here. This with respect to U2, we did this wrong. So check, let's do it again. So with respect to U2, nothing here, nothing here, nothing here, nothing here, right here, minus K2 U3, okay, that makes sense. Plus K2 U2. Oh, hold on, we're doing it with respect to U1. No, we're right. So look for U1s. There's nothing here, right? So that means we are good. 0. My bad, I got confused for some reason. But no, we're right. F3x. Is there any U1s here? Yes, there is. There's one right here. And that's it. Just right there. Okay. And then F4. Is there any U1s? No. So it's 0. Okay. Now I'm just going to go ahead and put U1, 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 U1. Next term, do the same thing for all the U's. So now let's do U2. There's nothing here, right? So we're gonna put 0 for U2. There's no U2s. In the second equation, there's a positive K2 for U2, and that's it. Just right there. Third equation, is there a U2? Yes, there is. It's not here, here. There's one right here, and that's about it. Negative K2, right? It's a negative in front of it. And then for equation 4, there's 0. Nope, no U2s. So U2, 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 and U2. Next one. Now we're doing U3s. U3s at the first equation, yes there is. There's a negative K1. Put that. And that's about it. Close it up. Second one, there is a U3 right here. That's a negative K2. And if it helps you I mean, it doesn't help me, but it might help you, just cross them out every time you finish one, right? Cross them out so you don't get confused. I guess you might be confused, but either way, we're gonna verify this. So you don't even have to trust your, I don't even know what kind of skill this is, right? Just looking at it, but we're gonna verify the matrix once we're done. So U3 at the third equation, there's one right here, is a K1. So we'll put K1, another one, K2, plus K2, minus, no, I thought that was in, oh yeah, plus K3 right there. K3, and that's it. There's no more U3s. Finally, in the fourth equation, there's a negative K3 only, so we'll put negative K3. And all these are U3, 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 and U3. Finally, the last one, U4. There's 0 in the first one, and there's 0 in the second one. So we'll put 0, 0. Okay, U4, right here, negative K3. And finally, K3 right here for the fourth one. So close it up. And these are U4s. And that's it. We're near the end. So now we're just going to assemble the matrix. So let's go ahead and do that. F1x, F2x, F3x, and F4x. Okay, so we're just gonna go ahead and fill in the matrix, just the K's, because we're gonna do the U vector after. It's a D right here, but it's actually a U. Okay, K times U. All the K's, so it's K1, 0, negative K1, 0. K1, 0, negative K1, 0. Next one is K2 in this position, negative K2, 0, and 0, right? 0, K2, negative K2, 0. Next one is negative K1, negative K2, these three, and then negative K3. So I'm going to go ahead and do this one first because it's the biggest, plus K2 plus K3, negative K3, negative K2, and negative K1. Finally, last one, negative K3, K3, 0, and 0. Cool. So this is the answer, right? U1, U2, U3, and U4. That's the answer right there. Now let's go ahead and verify it real quick using the other method, the direct stiffness method. So this is nodes, right? We know this is nodes 1, 2, 3, and 4. 1, 2, 3, and 4 row columns, or C-cola if you watch the other videos. Let's go ahead and do each one by one. So let's do K1 first, okay? K1. It's between nodes 3 and 1. 1 and 3. So K1 is between 1 and 3. So we go 1, 3, then 1, 3. So this position, this position, this position, this position. Should be K1, negative K1, negative, positive. Okay, that K1's positive. So that means spring 1 is verified. Now let's do the second one between nodes 2 and 3. So 2, 3, 2, 3, and these 4, K2, negative, negative, positive. So boom, that one's verified. Now finally K3 is between nodes 3 and 4. So 3, 4, 3, 4, positive K3, negative, negative, positive. Boom, that means we verified all of them. We did this problem correctly. Now check the description if you want to keep going. I'm gonna stop right here because I'm just duplicating efforts at that point. I'll just put the other video, but that is how you do it using the potential energy. And you know, this really is a long way because we did all this just to get here, but using the direct stiffness method, this pretty much is step 1. You'll see in the other video. This is just like another way of solving it. I wouldn't do it, but you might get quizzed on it, so study this, you'll be all right.